Hello, good evening everyone. My name is Abhinav Gupta and I am a PhD student at University of New Hampshire. This is a joint work with my advisor Professor Redeem Bartos. My research is focused on QUIC and HTTP3 and how to improve protocol performance. I'm also interested in investigating the performance of different protocols in different network settings. We have done this experiment for evaluating user experience of HTTP3 in different real-world deployment scenarios. Now let's talk about QUIC. Quick was introduced to improve performance and quality of experience in poor network conditions and to reduce latency. Google was first to come up with Quick, which is also known as GQuick. Quick was recently standardized by IETF in RFC 9000 last year. HTTP3, an application layer protocol, uses Quick as transport layer. Quick introduced zero round trip time to reduce latency along with other features such as multiple independent streams and connection ID. Quick offers both 0 RTT and 1 RTT connection setups. The 0 RTT handshake only works if there has been a previous connection. If the client and server are geographically distant, each round trip time can take over 100 milliseconds, so having a 0 RTT connection helps in reducing the latency. Since Quick uses multiple independent streams, it avoids head-of-line blocking caused by waiting to recover lost packets. The connection ID acts as unique identifier for the connection, which is used to ensure that changes in addressing at lower protocol layers will not cause packets to be delivered to a wrong recipient. One of the other important features of Quick is that it is implemented in user space, which enables easy changes and quick deployment of the protocol. Now let's look at some of the previous work. We all know that performance has been an issue since the inception of World Wide Web. Recently, there has been an increase in latency-sensitive applications and web latency needs to be reduced. There have been studies in the past about QUIC and HTTP3 in artificial networks, but there have been a handful of quality of experience studies on QUIC and HTTP3 in realistic networks. Researchers originally started exploring the performance of QUIC by studying the page load time metric. However, with the advancement in internet technology and web pages, the researchers are now shifting the focus towards quality of experience. R. Das was the first to do quick performance study in 2014, and his study was based on page load time. Some of the other page load time studies were done by Biswal and Cook. Furthermore, some of the other interesting studies on quality of experience were done by Seifert, Trevisan, and Saf. We extend the SAF's work to realistic network scenarios and use more implementations to do the study. We investigate the performance of a protocol using two metrics. Firstly, we measure the quantitative throughput of various servers in different network settings. Secondly, we measure the FCP, also called as first contentful pane metric of the Lighthouse tool. Now we look at the goal of our experiment. In our experiment, the goal was to do an empirical study of quality of experience under realistic network scenarios. We see how local connectivity, server locations, and server software impact the protocol performance among different HTTP3 and HTTP2 servers. The experiment was necessary to understand how well the new protocol performs in different realistic scenarios and compare the results with highly optimized HTTP2 implementations. Now let's look at performance metric. We measure the throughput by downloading a file from server using Chrome browser. FCP determines the time it takes for the initial document object model known as DOM content to be loaded on the browser screen and is more oriented towards quality of experience. FCP metric was preferred to analyze the quality of experience of the web page since page load time alone does not give comprehensive analysis of quality of experience. In order to measure the FCP time, a simple static web page with images and JavaScript was hosted on different HTTP3 and HTTP2 servers. Let's see how our testbed is structured next. Combining two local connectivity, wired and wireless, and three server locations, LAN, which is same as local network, regional and global, we get a total of 6 scenarios, which are referred to as local wired, local wireless, regional wireless, global wired, and global wireless. The local wired scenario replicates no impairment scenario. Regional server, which is hosted in central India, corresponds to typical server location for content transfer to the audience. Global server, which is hosted in Eastern USA, represents a high latency network. Let's look at geographic locations of our clients and servers next. We see more specific details about client and servers here. Client was hosted in northern India. As said previously, servers were hosted in local, regional, and global locations. Local servers are hosted on a local machine. Regional and global servers hosted using Microsoft Azure virtual machines. Regional server is located in Central India. The global server is in East US. Ping and traceroute utilities were used to calculate the base latency and hop for regional and global servers from the client machine. The regional server exhibited approximately 40 millisecond latency and 19 hops, whereas the global server exhibited a latency of approximately 230 millisecond and 24 hops. Client to server physical distance for global scenarios approximately 7.5 times more than the regional scenario. Next, we will see how our testbed looks. In the wired setup, the client, local server, and wireless router are connected using wired gigabit Ethernet switch. The left side of the figure shows how it is connected in the wired setup. Now we look at the wireless testbed. Whereas in the case of wireless setup, the client and local server are connected using wireless router. Here also we can see on the left side of the figure how it looks on the wireless setup. Next, we see the tested servers. HyperF was used to measure the baseline throughput. HyperCon, Nginx, AIOquick, and Quiche servers were used in the experiment. HyperCon and Nginx support both HTTP2 and HTTP3, whereas AIOquick and Quiche are HTTP3 servers. HyperCon uses AIOquick to provide HTTP3 support. Certificates from AIOquick and Quiche were used for HyperCon and Nginx as well. There are two implementations available for Nginx which support HTTP3. One is the implementation which uses Quiche to provide HTTP3 support, and the other implementation is Nginx's own quick implementation. Nginx's own quick implementation was preferred because the preliminary experiments performed on Nginx Quiche showed that the server had stability issues in real networks. Now let's look at how we measured the performance. For measuring the performance, the client machine ran the Chrome browser to download a 50 megabyte file to measure the throughput, and the Lighthouse tool was invoked to measure the FCP metric. Chrome and Lighthouse both support the HTTP3. To avoid having observations impacted by caching, Chrome browser was started in incognito mode. Lighthouse clears caches by default for every audit. 10 iterations of each scenario were measured, and then the average value was finally considered to minimize the variance. In order to measure the FCP time, a simple static web page with images and JavaScript was hosted on different HTTP2 and HTTP3 servers. The web page had no videos or multimedia content. There were no external scripts or content loaded from the web page. The web page specifications are given in the table. It was preferred to use a static web page in our study to maintain consistency between experiments and to avoid the effect of dynamic content in production web pages. Next, we look at the results. As said before, baseline throughput observation was established by HyperF. In these graphs, we see the throughput results. We see throughput for each scenario in the left figure, and we see the same data in the right figure, which is organized differently. The first one is grouped by scenario, and the second is grouped by server. It is seen that closer the client and server are, the performance is better. Local connectivity also has an impact. It can be seen that wired scenarios are better than wireless scenarios. In the right figure, we also see that different servers show huge differences in how they perform. It was observed that Nginx HTTP2 had the highest throughput in local and regional scenarios. However, Quiche HTTP3 had the highest throughput in global wireless scenario. Nginx HTTP3 throughput dropped from local wired to global wireless scenario considerably, whereas throughput of other HTTP3 servers did not dip so drastically. We see that HTTP2 throughput fared better than HTTP3 in all scenarios, with Quiche being the exception in global wireless scenario, as said before. HyperCon HTTP3 turns out to be the most underperforming server. It was found that most HTTP3 servers did not perform well in local and regional scenarios. Quiche HTTP3 had a stable throughput as compared to other HTTP3 servers. Next, we look at throughput relative to HyperF. This figure shows us the throughput of all the protocols relative to iPerf. It is seen that all are below 100%. In some cases, relative throughput of server is single percent of iPerf. For example, HyperCon HTTP3 in local wired scenario and Nginx HTTP3 in regional wired and global wired. Next, we see the FCP results. In these graphs, we see the FCP results. We see FCP for each scenario in the left figure, and we see the same data in the right figure, which is organized differently. The first one is grouped by scenario, and the second is grouped by server. Lighthouse FCP metric results were generated in JSON format. The lower the FCP time, the better is the performance. We see how the FCP time goes up when the client and server distance increases. In the right figure, we also see that different servers show considerable difference in FCP time. It is observed that Nginx HTTP2 takes the least FCP time in all scenarios, except in case of global wireless scenario where Nginx HTTP3 outperforms all other servers. AIO Quick and Quiche perform similarly in case of local and regional scenarios. However, in global scenarios, their performance is not competitive. HyperCon HTTP3 had the worst FCP time in all the scenarios. There is a considerable difference in FCP time among the HTTP3 servers when it comes to the global wired and wireless scenarios. Nginx HTTP3 takes the least FCP time, followed by Quiche HTTP3 in global scenarios. However, HyperCon HTTP3 and AIO HTTP3 do not perform well. Other lighthouse metrics were also recorded. For speed index, it was observed that Nginx HTTP2 was always leading, followed by HyperCon HTTP2 in most of the scenarios. HTTP2 largely outperformed HTTP3 for speed index. Nginx HTTP2 had the best largest contentful paint. HTTP2 performed better than HTTP3 for largest contentful paint metric. It was seen that time to interactive scores had a similar trend as first contentful paint scores. Total blocking time was 0 milliseconds for all servers in all scenarios. Cumulative layout shift scores less than 0.1 are considered good scores, and it was observed that all servers had a cumulative layout shift scores of less than 0.1. Next, we go to our conclusion. To conclude, we measured the throughput and FCP in diverse scenarios and observed that for HTTP2, the servers with high throughput also had high FCP score, that is low FCP time. Hence, throughput and FCP for HTTP2 correlate with each other, whereas in case of HTTP3, no discernible pattern is found. The only exception was found in case of global wireless scenario, where a correlation is observed between throughput and FCP for Quiche HTTP3. Though HTTP2 performed better than HTTP3 in local and regional scenarios, it is also to be noted that HTTP3 and quick implementations are experimental and still getting fine-tuned, whereas HTTP2 implementations are highly optimized and are production-ready implementations. Performance gain in HTTP3 in more challenging network conditions in the global wireless scenario seem to be due to the advanced quick protocol design and features such as improved stream multiplexing to prevent the head-of-line blocking and optimized congestion control implemented in user space, which allows faster handshakes. Next, we look at our future work. To extend the present work, more detailed analysis tools will be added so that the root cause of low throughput and FCP scores can be identified. Specifically for HTTP3, QLog integration is planned so that the functioning of various streams can be studied in more detail. More complex web pages with videos will be integrated to test the performance of HTTP2 and HTTP3 servers. Our future research will include quality of experience analysis of HTTP3 and HTTP servers in mobile networks and devices. More server implementations will be added and experiments will be tested on more browsers. Thank you. Please let me know if you have any questions.